Andrew. I'm from oh, all right. I'm from the United States. I wrote problem two on the pre-TST. Uh, the that apparently I was apparently didn't get any full solves, but it's all right. Um, yeah. So I guess this lecture is going to like presuppose like a sort of base level familiarity with functional equations. Um, but if if um if any of you need kind of like a refresher, oh, this is green. Right, if any of you need kind of like a refresher, functional equations, the sort of the basic idea is um the basic idea is you have some sort of equation and a a domain and codomain. For example, you're given that f goes from like reals to reals or something, and it satisfies some sort of equation in terms of f. For example, f of x squared plus f of y squared equals to like f of x squared plus f of y squared or something like that. And the way that you solve it is by plugging in specific values of x and y and trying to exploit that like sort of properties about this equation in order to figure out what f is for all values of x and y. Generally speaking, you can't assume any properties about x like that about f like that it's continuous or additive or monotonic or anything like that. Specifically, I see what happens is a lot of people assume that f is a polynomial, and this is usually like automatically 0 points, which is very sad. Um, Especially if it's, an earlier question. Um, yeah, but when it comes to functional equations, there's like a few like basic like early game strategies, like early steps. Um, Usually what you start out by doing, especially in positive real numbers, is well, obviously the notation that I'm using is we have p of x and y denote the assertion of plugging in like a specific x and y into the functional equation. So the early steps usually, we usually, plug in sort of special values of x and y. If it's like in real numbers, you'll plug in 0, but if it's in positive real numbers, you'll plug in stuff like 1, 1, like 1x, uh, x1, stuff like that, like x, y. Um, these kinds of plugging in values, they usually don't like solve it immediately, but they'll give you some useful information specifically about the value of p of 1, or whether or not you have some sort of like an involution, things like that. There's also the strategy of like exploiting symmetry by plugging in stuff like p of x and y, and comparing that to p of like y and x, to try and like see if you can like get some sort of shared values within the equation so you can subtract them. And also in early ideas to like just guess the function so you know what to look for. But like once you have these like first basic things down, a lot of the time you'll get something that kind of looks closer to the solution, but usually this won't solve the problem immediately, especially if it's like an international math Olympiad level problem. So after that, if we're talking about positive reals to positive reals, there are a few sort of basic techniques to try and take you from here, and many different problems use more than one of them. For example, as shown in the handout that I think was posted in the general chat, a very common situation is where you have like where you try and force some inequalities or sequences in terms of f in order to get sort of uh, specific properties about the function, like it's monotonically increasing or where it's decreasing for certain values. Um, then there's using injectivity, surjectivity, and especially one thing that I've seen is very common is trying to prove additivity. Uh, uh, Additivity. Now, the thing with additivity here, which basically means like you end up forcing something of the form f of x plus y equals to f of x plus f of y. If you can force something like this, and you know that f of x is, bounded in the positive real numbers, this equation actually implies that f is always equal to some constant times x for some constant c. Um, this was actually the first question in the lecture handouts, and sort of uh, oh, hmm, I guess. All right. Maybe yeah, okay. And to like, oh, I guess I could do this and that. Hmm. That didn't work. Okay. Um, yeah. Oh yeah, and usually like another big early game strategy is to try and plug in specific values that like cancel out certain things on either side. Um, Yeah, so this proving this over the positive reals is one of the first probably yeah, this was the first thing on the handout. And basically the way that you do it is by noting that this also implies that f is increasing, and also like this implies that f is always equal to cx over the positive rational numbers. And so because the rationals are compact, you know that this is also satisfied over the reals. Like you can complete the domain. Now,
Yun o, yung futsi.
um, okay, so uh, usually, hmm, I guess hmm, okay,
I
I'll
think you
move that
can
around.
pan, yes. Yeah, yeah. That's
Uh,
better.
hmm, sorry, I don't have a lot of familiarity with the Zoom whiteboard. Okay. I mean, I guess
I
it's
mean, you could use a different one. Is it? I mean, it's not necessary that you use Zoom whiteboard. So
um
okay, if you have access, like if you can use the Miro or something like that, then that's fine as well.
I mean, do you know how to just pan down?
Well, if you're on the laptop, perhaps like two or three fingers, and you just drag them. Is it something like that? Are you on laptop?
Yeah, I
Then
think
go to touchpad, and then maybe two or three, just put three fingers in there, or I think two fingers, and then just span, like just scroll it.
it
Does that
doesn't
work?
seem to be working for me. Um, I
Okay.
don't know if I mean, I guess I'll
Yeah,
just
yeah, it's fine. Yeah.
all right. Um, so now while there's a lot of techniques, I guess I'm going to be focusing mainly on the two sort of big ideas of additivity, uh, which is similar to like reducing to and injectivity. Now, for additivity, a lot of the time, this will come up if the equation kind of looks like, if it kind of looks similar to the function equation, but you can kind of there's sort of a little bit of a little bit of issues with it, like if something is like unwrapped and you need to try and uh, kind of uh, maneuver into a different form. For example, the second question on the handout from the Princeton University math competition, it was of the form f of x plus y plus xy over x plus y is equal to f of x plus y plus f of x, f of y over x plus y. And this is over the positive reals. Now, when you see something like this, you can kind of see that I mean, it looks like it could satisfy the Cauchy's functional equation. Um, oh, hello. Um, all right. And so the sort of strategy here is to well, so first off, right, the early game strategy um, trying to exploit the symmetry of the left-hand side by plugging in P of xy and comparing to P of yx. This gives you f of x plus y plus, oops, x plus y plus xy over x plus y is equal to f of x plus y plus f of y, f of x over x plus y. Now, you'll notice that like the left-hand side and these x plus y, this is shared between uh uh is wait, is that actually math, Louise? Okay, sorry. Um yeah, this we need to have basically that f of x, f of y over x plus y is equal to f of y, f of x over x plus y. Now, um, I think I should probably I can I should probably just use I'll just use like this whiteboard because I'm having a lot of trouble panning on this one. Um, I should hmm. Yeah, I mean I wait, could you try wait, am I could you try making me co-host? Maybe there's specific whiteboard permissions.
Yeah, I think you're already co-host. Uh,
Oh,
I can
um,
make you host though.
okay, well that's yeah, I should okay, I'll stop the share and then just move to yeah. Okay. All right. I can all right. So sorry about that. What we have what we have is f of oh, it's a lot thinner. Uh, uh yes, a d
So I was wondering, is it maybe a good idea to make a change of variables as keeping some variables um, as x plus y as say u and xy as v maybe?
yes, this is a very good idea for this problem. So um so after we get like something of the form like f of x, f of y over x plus y equals to f of y, f of x over x plus y. And we kind of And we note that like this x plus y can kind of be really can kind of be anything. Um, what this gives us is something of a form like f of u plus b over u for specific values of v. Like v can't be so like the issue is because of like AMGM inequality. You can't have any two values of x, y, and x plus y. Um, this ends up giving you uh, I believe uh, yeah, so this ends up giving you something very, very useful. But to flesh that out, when we expand from this, we basically get f of x over f of y equals to f of y over x plus y over f of x over x plus y. And for any, or sorry, x and y. And what this means is really that this ratio, the ratio between any two values of this function, is wholly dependent on the ratio between the two variables in question. And the reason for that is because we can kind of shift
Oh,
this
because
value.
like this is a homogeneous sort of thing, like homogenizing in bicentric coordinates, kind of like that.
Yeah, it's basically homogeneous. Like what happens is if you multiply both the numerator and denominator by some specific value, then you can shift both sides of the equation to get effectively that f of a f of b um, is equal to f of one f of a b. And the function is basically kind of multiplicative. It's multiplicative but shifted by a constant. So if we let f of 1 uh, be some constant c, then we have for all a and b, we have f of a, f of b is equal to c f of ab. Um, now, when we plug this, now basically, now if we let our variables be x plus y equals to say u and xy over x plus y equal to um, say v, right? And I know that we could have let x, y be u, but this kind of makes it a little bit cleaner. We basically have that we're given that v is greater than or equal to 4u, I think, by AMGM inequality. I could be a little bit off on that because when you have x plus
Should be the other way
oh,
around because
uh,
XY is on the V side.
mm, yeah, sorry. Yeah, v
So
is
then
is greater than or equal
4V should be less than or equal to U.
yeah, less than or equal to you. Sorry. Um, right. So then if we have some arbitrarily large value of this yeah, so we have okay, yeah, a greater than or equal to okay. Um So if we plug in some arbitrarily large value of m greater than or equal to 4 times x, wait, this should be sorry. Basically, we have that for any a and b, we have if a is greater than or equal to 4b, which is greater than or equal to 0, then f of a plus b is equal to a plus uh, c times f of b uh, by taking x plus y being equal to a and xy over x plus y being b, right? Because um, by AMGM inequality, right? X plus y squared is, or sorry, x plus y over 2 is greater than or equal to square root of xy. So x plus y squared, oops, x plus y squared is greater than or equal to xy. And so, or sorry, 4xy. And so x plus y is greater than or equal to 4 times xy over x plus y. Now, what this means is that if we ever have this kind of situation, we have that a plus c times f of b is equal to f of a plus b for a greater than or equal to 4b, the greater than or equal to 0. And so to finish, if we look back at the original equation, we have f of x plus y plus xy over x plus y is equal to f of x plus y plus c times f of xy over x plus y, which gives us this. And so if we have some arbitrarily large value of m greater than 4 x plus y, what we can do is we can have f of m plus x plus y, uh, and this is equal to f of m plus c times f of x plus y. But if instead we look at it as f of m plus x plus y, this is also equal to f of m plus x plus c f of y. And if we expand this one out, this is equal to f of m plus c f of x plus c f of y. And we miraculously get that c f of x plus y is equal to c f of x, the c of f of y. And so this function has to satisfy the additivity, the Cauchy's functional equation. And so this kind of reduction going on, where we try and prove a fundamental fact about the function that allows us to get down to Cauchy's functional equation for arbitrary values of x and y, is very common and very useful in these kinds of functional equations over the positive reals, because of the aforementioned this implying that f of x is linear. Now, obviously, you're not done from here. You have to show that the only value of like kx for like f always equal to kx is like k equals 1. But this is not very difficult to show once you have this, because you can just plug it back into the original equation. So yes.
So one more idea that we see from here is the idea of looking at a certain expression and then looking at it in multiple different ways, like we did over here with m plus x plus y, where first we looked at it as m added to x plus y, and then we looked at it as m plus x added to y. And similarly, we also have the triple involution trick, which also falls into a similar category, I believe.
Yeah. I mean, these are both very common themes. Really, like positive, like functional equations. There's not a whole lot of theorems, but there's a lot of techniques that you kind of have to use like in sequence. And so it can be very difficult to try and practice for them a lot of the times, because it's very dependent on like just familiarity with the subject. I'm going to go over one more problem that uses additivity, and then I'll move on to some injectivity based problems. But these are just broad categories, really. I think that a lot of the times it uses both, and it also, like functional equations also often use inequalities of functions to prove either additivity or injectivity. The reason that I'm probably going to steer clear of talking about inequalities is mainly because it seemed like this is very common in the PDF handout that was dropped in the general chat. Now, the second question comes from IMO short list 2007. And this one says f of x plus f of y is equal to f of x plus y plus f of y. Now, looking at this, you can kind of guess that the function f of x is always equal to 2x, right? This kind of like would make sense if you plug it in. it works. But it's a little bit difficult to show just based off of this that f of x satisfies additivity because there's not a whole lot to get, right? So um first off, right, knowing that the function is f of x equals 2x for all x, you can kind of this is kind of how you motivate the idea of looking at g of x equals to f of x minus x, and then looking at the equation based off of g of x. Now, um, if we let
Actually,
p,
related to that, I just looked at the problem and my first claim was that f of x is, I believe, greater than or equal to x. So
yes,
I believe that could further motivate it. And the reason that this claim comes up is because you try to use the same cancellation idea. And the idea is that you try to forcefully substitute x equals to y minus f of y, which would give a contradiction. So y minus f of y has to be less than or equal to 0, or in other words, f of y is greater than or equal to y.
if you have any kind of situation like this, then you would get an f of y on this side and an f of y on this side. So this would have to be equal to 0. So that is correct. Um, and so because f of x is always greater than x for all x, um, or I guess this would show that it's greater than or equal to, but if it's equal to x, then you can plug in p of x0 to get uh, or p of y for which f of y is equal to y, to get the left hand side getting f of 2y and the right hand side having this be equal to f of 2y. So you can get the same thing. But yeah, so g of x is always greater than 0. So basically, what this means is g of x is also defined on the region r plus to r plus. Um, yeah. So if we try and uh, if we plug in like p of x minus y comma y, what this gives us is f of x minus y plus f of y is equal to f of x plus f of y, right? And if we sort of plug in if we plug in g instead, right? Like if we substitute f out for g, what we get is g of x minus y plus f of y, um, plus x minus y plus f of y is equal to uh, uh, sorry. Oh yeah, compare here. G of x plus g of y plus x plus y. And so this is equal to, um, I'm sorry. So when we plug this in, again, what we get is, uh, yeah. So what we get is g of x plus g of y plus x plus g of y is equal to g of x plus g of y plus x plus y, and we can cancel out here, and we can cancel out here to get g of x plus g of y equals to g of x plus y. Now, this looks very good, right? And what you can actually get from this is that g is injective. Can anybody see why this gives us that g is injective?
If we assume that g of a equals g of b, then just substitute y as a and b respectively, and then like it just comes out on the RHS.
Yes. We get basically that the right hand side is going to be different and the left hand side is going to be the same. Now, if we just let's just let q of xy denote this special assertion. Um, and uh, and we're given that x is greater than y, because otherwise g would not be defined. Because g is from positive reals to positive reals. Now, if we have that x greater than y greater than some k, um, then we have given this g of x plus g of k plus g of y minus k is equal to g of x plus g of k uh, plus y minus k. Because by plugging in q of x plus g of k, comma y minus k, giving that. And we also have that this is equal to, oh, a little bit, all right, g of x plus, and moving around, g of x plus k plus y minus k uh, is which you can cancel out to get g of x plus y. Now, what this gives us is because of injectivity, right? Um, we have that x plus g of, all right, yeah, and this is equal to g of uh, x plus g of y, given because of just q of x comma y. So we have two g statements on either side of this, right? And so what this gives us is, because of injectivity, this g statement has to be equal to this g statement. And that gives us x plus g of x plus g of y minus, sorry, x plus g of k plus g of y minus k is equal to x plus g of y. And so again, we get g of k plus g of y minus k is equal to g of y. And that gives us additivity. And so g of x has to satisfy Cauchy's functional equation. When you solve for g, you can plug in g just being some c times x. And you can do the same thing for f. And so you're done. Now, okay, this was a difficult example. And the motivating step behind this, and once you substitute in g, plugging in sort of obvious values of x and y, common special values like x minus y and x and y, it becomes a little bit easier to see how this might be motivated, but this is still like quite a difficult problem because there are a lot of directions potentially to go. I think that this inequality that f of x is always greater than x is very helpful. But overall, this is not a super easy problem. But the fundamental step is to try and figure out something of the form uh, like x plus y, g of x plus g of y is equal to g of x plus y for some values of x and y. Here it would be k and y minus k. Now, so this is sort of a taste of the kinds of problems that involve reducing to Cauchy's functional equation. Um, and this is perhaps one of the more common techniques. Aside from inequalities, I think that the other like very common technique I often see is leveraging injectivity in certain situations. Um, for this problem, like for the IMO shortlist problem, injectivity was used close to the end, but it was only to show that G was additive. Um, so I'm going to show a couple of examples of problems where injectivity is like very is like the main thing, um, or at least like a very important thing. And it's sort of proving injectivity is sort of the main step. So the first problem from the injectivity side of the handout is a little bit more introductory when it comes to these problems of using injectivity. We're given f of y over f of x. Oh, and this is from Japan, Math Olympiad 2019, problem 3. Plus 1 is equal to f of x plus y over x plus 1 minus f of x. Now, you might notice that this kind of looks like Cauchy's function equation, but this is as far as I know, like it's very difficult to use Cauchy's function equation on this one because of the wrapped values of f. Um, yeah, but um, so if you plug in like easy values of x, you'll notice right away by p of x comma x that f of 2 is equal to f of x plus 2 minus f of x, right? Um, and so like that gives you something, and you can, and if the question was over the even integers, you'd be done. But the question is not over the even integers, sadly. So from here, what you can do is you can try and show injectivity. Now, to show injectivity, there are a few main ideas. Sometimes these are a little bit more involved, using like trying to use inequalities or things like that. But a lot of the time, showing injectivity basically just comes down to showing to taking like specific values of p, for example, p of a and b for f of a is equal to f of b. Taking p of a and b and comparing it to p of b and a, or something like p of xa versus p of xb, or p of a x versus p of sorry, bx, stuff like that. Now, here, all right. So for this problem, uh, sorry, does anybody have any good guesses on how we might try and show injectivity?
I mean, if we have f of a equals f of b, then just plugging in both of a and b gives you a very similar equation to what we've just obtained. Like
Um,
we get f of 2 equals like f of a or f of b. I mean, f of 2 plus f of a equals f of a plus b over a plus 1. But it's also f of a plus 2, and this might help.
um, yeah, I mean, so, um, if we do this, right, like where we plug in P of A comma B, right, you'll notice that like this, like once you move it over, this is actually going to be the same as if you plugged in F of P of B comma A, right? So like you can get like this equals to F of B plus A over B plus 1. But from here it becomes a little bit more difficult, right? Like because
Yeah,
if you
because
can use
like a
this,
and b are
sorry,
fixed, so there's
yeah,
not much freedom.
yeah.
Oh.
Um, but that is a good thought. The fact that these are fixed implies that we might want to introduce like a free variable uh, into the oops into the expression. Um, yeah. So what happens when we plug in p of a comma y versus p of b comma y? Like what does this give us?
F of a plus y over a plus 1 equals f of b plus y over b plus 1.
Yes, f of a plus y over a plus 1 is equal to f of b plus y over a plus 1. Oops. Now,
Y over b, right?
yeah, sorry, y over b. Right. So, you'll notice that um, we have this, right? And we have that f of x plus 2 minus f of x is always going to be a fixed value that's not 0, right? So is it possible to just like select y so that this is going to lead to a contradiction?
Okay, immediately my mind goes to finding some sort of y so that the difference between the two internal quantities here is 2.
Yeah. Um, so now what you can do is you can just like so if we assume that like b or that a is greater than b, right? If we can choose a b such that like y over uh, y over b plus uh, b is equal to 2 plus a plus y over a, then yeah, then we should be actually probably should do it the other way around, right? Um, actually no. If yeah is equal to 2 plus a plus y over a, then we should be good. So, yeah, so miracle. So the thing is, this only gives us that it's injective when you're looking at like when you're looking at terms that are like have a difference of two. For example, if you had uh for example, I don't know, f of x is equal to x plus or no, is equal to uh like the floor of hold on. F of x is equal to like the floor of x. This would actually also satisfy this equation, because uh, yeah, because like f of 2 is going to be equal to 2, and the floor of x is going to like this is not going to be an injective function, but like the floor of x plus 2 is equal to 2 plus the floor of x for all x. But like if we're just looking at integers, like or at least even integers, then that would solve the problem. Now, yeah, so if we just have like if we just like if you just like manipulate this, so we have like um y over b minus y over a is equal to uh 2 plus a minus or I guess we could just have this be 2k, because if you plug in like if you repeatedly plug this in uh multiple times, you would still get that this is positive. So we have this for like some integer k, um 2k, right? Then you basically just have like y times a minus b over ab is equal to 2k plus a minus b. And because this is some fixed value and this is also some fixed value, and all you need is for y to be like arbitrarily large for this to be an integer, you're guaranteed that you can select some y. You don't have to like show which y it is. You just need to show that like it does exist. Um, yeah, but like basically because like if you know even for like very close values of a and b, you can just select y to be like very large, and like that will give you something. You don't actually have to show like what the value of y is, but you certainly can do that if you just like if you take a if we take like a y such that like or if we take k such that like this expression is larger than this expression, you can just divide both sides. So it's not super clean, but you can still get a contradiction based off of this. Just by taking a y such that like b plus y over b plus 1 is equal to some like or wait, this be b minus a? Oh no, a minus b, yeah. This is equal to like some multiple of 2 more than this. And you can see why we can just repeat this multiple times. So is everybody clear on this idea? It's a little bit like okay, okay. So once we show that y is injective, or that f is injective, what we can do is we can plug in p of 2 comma y to get um, f of y over f of 2 plus 1 is equal to f of 3 plus y over 2 minus f of 2, right? Um, so like this just comes from plugging it in. Um, and we also have that, and so we have f of y over f of 2 plus 1 plus f of 2 is equal to f of 3 plus y over 2. And we know because of this expression um, that this is equal to of f of y over 2 plus 3, which is equal to f of 3 plus y over 2. And because of injectivity, we get, sorry, it's f of 2. Because of injectivity, we get f of y over f of 2 is equal to y over 2. And cross multiplying gives you that y is linear. And you can actually show that like this is satisfied for all constants c. So we have like f is like cx for all x for some constant c. Um, Now this was sort of just like a basic application of trying to show that it's injective by forcing some variables together. Some problem.
Andrew, Prajit Dai is asking in the chat if you can make him co-host.
Oh, I'm sorry. I have to go to participants. All right. Um, okay. Yeah. Thank you. It's hard to look at the chat because it's all the way on the top. Um, But there are some situations where proving injectivity is kind of easy, but the application of it is not super easy. Um, so for an example of this, and I guess I mean I'm not sure how long this is supposed to go on. Um, I'll look at like a problem from 2 years ago, USAMO, USA Math Olympiad, um, USAMO 2023, problem 2. Where basically we have f from positive reals to positive reals, and we need to show, and we're given that f of xy plus f of x is always equal to x f of y plus 2. Now, is there, so how do we show that f is injective, like just right off the bat? Is there anything that we can plug in that would give us that?
Yes, I believe there is.
What do you plug in?
Uh, well, if we plug in firstly x equals a and y equals b, or rather p of a comma b, And then if we plug in P of B comma A, then we get that F is injective.
Right. So to flesh this out, what we get is f of AB plus f of A equals to A f of B plus 2. But this is also equal to B f of A plus 2. And so because these are equal to each other, we get A equals B. Now, so given that f is injective, it's a little bit difficult to see what to do from here. That's why this problem is actually like very, very difficult, I would say. Um, like because it's not difficult to get to an equation that should give you the solution, but it's very difficult to see like why it does give you the solution. So if we plug in, and I'll just like say exactly what to do in the interest of time, because I think I added this kind of at the last minute into the document. If we plug in p of f of x comma y, and we look at that versus p of f of y comma x into the original equation, what we get is uh, f of x y plus f of x is equal to f of x f of y plus 2. But this is yeah, this side is actually symmetric. So you can swap the variables to get f of uh, x f of y plus f of y. Um, and then you can use injectivity to show that f of x y plus f of x is equal to uh, f of y x plus f of y. Now, it's not super easy to see, but this is actually sufficient to show that f is a linear function. And the reason for that is because of it's actually because of geometry. Um, and this is a very beautiful solution. Uh, so we're given that, so we have that f of x, that y f of x minus x f of y is equal to f of y minus f of x. Now we can actually, so what you do to show this is by subbing in like three different variables cyclically. So this is like p of x comma y. If we do p of y comma z, we get z f of y minus y f of z is equal to f of z minus f of y. And p of z comma x gives us x f of z minus z f of x is equal to f of x minus f of z. Right. Now, if we sum up these three equations, what this gives us is on the left-hand side, we get 0. And on the right-hand side, we get y f of x plus z f of y plus x f of z minus x f of y plus y f of z plus z of x. And so, does anybody know why this gives us that uh, f is always linear? I will give you a hint. Let's look at what happens when you look at the 3 points to find x, comma f of x, y, f of y, z, f of z. So there's a formula in coordinate geometry called the shoelace formula that says the area of a triangle defined by 3 points uh, that are like a or x1, y1, x2, y2, x3, y3. The area of this triangle is equal to the absolute value of x1, y2 plus x2, y3 plus x3, y1 minus x2, y1 plus x3, y2 plus x1, y3. And so what this actually gives us, this equation, gives us that for any 3 points, x comma f of x, y comma f of y, z comma f of z, uh, the triangle formed by the 3 points has area 0. And so they have to be collinear, which means that f has to be, yeah, this does come from the determinant. It's actually, I think the determinant like 1, 1, 1, x1, y1, x2, y2, x3, y3. And like the analogous formula for 3D, I think would be x1, y2, x1, y1, z1, like instead of 1, 1, 1. Yeah. And so any 3 points on on the graph of x comma f of x, uh, of like the graph of f of x, any 3 points are going to be linear, are going to lie on a line. And so you can show, therefore, that f has to be a linear function. And then you can plug this back in. Why wouldn't fixing y and z work here? Um, so I think that um, hmm, I guess if you have, so I think that probably would work if you fix y and z. Like if you have some constant c1 f of x plus c2 plus c3x is always equal to c4x plus um, c like c5 plus c6 f of x. The issue is that like and yeah, and you have this z and y and f of y, f of z. So you can choose y and z such that like given that f is not a constant function, you can choose y and z such that like uh such that these constants are going to be different. You actually do also get that f of x is linear. Uh, so that's yeah, I think that that would also work if you don't want to do this route. Yeah, but yeah, this so once you get that f is linear, all you have to do is like plug in f x equals to ax plus b for some a and b, and then plug this back into the original equation to get like f of x always equal to x plus 1. So this does this idea of cyclically summing is very interesting and unique. But I think that I honestly have not seen any other problems where this came up. Um, yeah, I'm trying to think if there would be any issues. Um, I mean, if you know that f of y is not equal to f of z, then like this does give you, right? Even if f of y does equal to f of z, it does give you a linear function. Yeah. Like when you if you if you allow one of the variables to move and like fix the other two, then you still also get a linear function. So maybe that's sort of this shoelace formula stuff is not required, but it is in my opinion a very very beautiful solution. Now, there are a couple more problems on the injectivity side. Um, I don't know if we should keep going. I know that it has been 1 hour, almost exactly. Uh, is there a specific amount of time that this is supposed to go for?
Well, not really.
Okay, I
Well,
guess
if you want to continue, you can. Otherwise, we could just wrap it up with some conclusion. But if you want to continue, you can. So it's not like there's a hard limit to time. So yeah.
okay. I guess I could show just for the sake of like parity. I could show just one more problem on injectivity. This comes from the 2016 IMO shortlist, and I think that this is sort of an in between where it's not super easy. Like you have to do some legwork before you show that it's injective, and like after you show that it's injective, it becomes a little. It's like not obvious. Uh, but we have um, so we have IMO shortlist 2016 A4. So we have f from positive reals to positive reals, such that for all x and y, uh, x and y, um, x f of x squared, uh, f of y plus f of y f of x is equal to f of xy times f of x squared plus f of y squared. Now, this is kind of a mess. Like it's a really big functional equation. Um, but what you kind of want to do here is you kind of want to like cancel a lot of stuff out, right? Um, so the first things that you can plug in, you know, p of 1, p of 1 x, p of like x1. What these give you, so when you plug in 1 and 1, you get f of 1, f of 1, plus f of 1 is equal to f of 1, f of 1 plus f of 1. And so, therefore, f of 1 is equal to f of 1. And so f of 1 equals 1. Now, p of 1 comma x, this gives you uh, f of x squared times f of 1, which is equal to 1, plus f of x is equal to f of x times f of x squared plus f of x. And p of x comma 1. Or no, that was, sorry. This, this is p of x comma 1. And then p of 1 comma x gives you uh, f of x times 1 times f of 1 plus uh, f of x times f of 1 is equal to f of x times 1 plus f of x squared. And like this cancels out. So you get f of x is equal to f of x, f of x squared. And you can plug this back into here. You have this is equal to f of x. So these two cancel out, and you have f of x is equal to x, f of x squared. Now, yeah, yeah, I mixed those two up. All right, so after that, after that, um, we have is f of x squared is equal to f of x. over f of x, right? And if you substitute f of x in for x in this equation, uh, you basically get again that like f of x is equal to f of x f of x squared, and so this is equal to f of x squared, right? Notice the subtle difference that's obfuscated by my poor handwriting. Um, so now I think we have enough to prove injectivity. So if we plug in the standard p of a comma y versus p of b comma y, and I should probably try and so if we plug in p of a comma y versus p of b comma y for f of a is equal to f of b, right? What this gives us is a f of a squared times f of a plus f of y f of a is equal to f of a y plus times f of a squared plus f of y squared. Now um, we can kind of uh, reshape the left-hand side. Um, yeah, this is this is equal to f of a y. Um, yeah, so since we have um, yeah, so we can reshape the right-hand side. This is equal to um, f of a times f of a uh, plus f of y f of a equals to f of a y times f of a squared plus f of y squared, right? Um, and now since we have that like this is equal to uh, right, so since we have that f of a squared is equal to f of a squared, this is actually going to be equal to f of b squared. So basically everything in this equation is identical except for this f of ay, right? So we therefore have that if f of a is equal to f of b, then f of ay is equal to f of by for all y. Now, so there are a few ways that you can go from here. You can plug in, so one way to do it is by plugging in, if we let this be like q of, I don't know, q of a, b. Uh, Actually, you need a place for the y. Q of y. Um, and plugging in y equals a gives f of a squared is equal to f of ab. And plugging in y equals b gives that this is equal to f of b squared. Um, and so we know that from back over here, we know that f of x squared is equal to f of x over x. So then we know that f of a over a is equal to f of b over b. And so this gives us a contradiction. We have to have that a equals to b. Now, from here, uh, all we really need is going back to the previous equation uh, of f of x squared is equal to f of x squared gives f of x squared is equal to f of x squared by injectivity. And this is equal to f of x over x. And so f of x is always equal to 1 over x. Now, this was kind of involved, I think. Like this, no, I don't think that any of the problems here are very easy or introductory. Um, so I apologize for that. But I also think that, um, forcing injectivity is generally like it's not usually as simple as just plugging in A, B, and B, A. And if it is, there's usually more to it than that. Um, like a lot of the times you'll also see situations where there's like breaks in injectivity and you can exploit those to get like an extra solution. Sometimes there's going to be like inequalities and sequences and stuff like that. So there's like a large number of techniques, and this was kind of just a sort of a taste of some of them. Um, but I guess the main takeaways from like these exercises, like the first is like uh, keep in mind that f of x plus y equals to f of x plus f of y. Oh, horrible at writing. F of x plus f of y implies f cx over. Hold on. I should rephrase this. Uh, if f define only on r plus to r plus, then this implies linearity. And also try to look at situations of A comma B such that f of A equals to f of B um, to show injectivity. All right. Those are the main, yeah, those are the main things to keep in mind. I think that um, these are sort of advanced techniques if you're already somewhat familiar with functional equations. I think that um, I think that it's these what you really have is like a list of kind of ideas to keep in mind. Things that are usually useful to plug in, and also like these are two main patterns that you want to look out for. So I guess I almost got through all of them. I don't think I'm going to cover the USMA 2022 problem. So I think that that's basically it. I don't know if there are any questions I can stay and answer them about any of these problems. But other than that, I'm pretty sure uh, this is this is this has been good. All right. All right. So I think I'll stop the share now.
Hi, yeah, thanks, Andrew, for doing this. Yeah.
All right.
Okay,
Thank
yeah,
you
that
for
was
having
fun.
me, for inviting me to do this.
Hmm. Yeah, I'll stop the recording.